Okay, on this example, they have this big function, and we're supposed to take the derivative, but then they tell us to do it using logarithmic differentiation. That's a good idea. That'll make it so much easier. What is logarithmic differentiation? Well, step one is you ln both sides, right? Notice this original problem does not have, there's no logs anywhere, no natural logs, no regular logs, there's no logs anywhere. So, and they're saying somehow we should use logs, like bring in logs that aren't even there to take the derivative. Exactly. It'll make it easier. Let me show you. So first step is you do the ln on both sides, like that. Now, why is that so great? Well, step two is you um, use the log properties. This is what you want to recall from pre-calc. That basically there's three log properties. Number one, if you have the log of x times y, that's room here, log of x plus log of y. And number two, if you have the log of x divided by y, that's the log of x minus the log of y. And number three, if you have the log of x to a power, that you could bring that power down and that power will just be multiplied to the front. So you want to use those properties. And so here we go in step two. So the left side, really nothing going on there. The right side, we have multiplied. So I can use this property right here. When you have multiplied, it's two logs added. So an ln is just a type of log. So it works for any log type. So it'll be then ln of x minus 5. And then that 2 can come down to the front multiplied. That's the third property. Powers come down to the front. Plus, again, the 3 will come down to the front. 3. But don't forget the ln of 3x squared plus 4. Do you see what happened there? Basically, things multiplied. So step one, we took the ln of both sides. And then when we have this, we can break it up real nicely. This is why it's helpful. Because if you have multiplied things, you make some two separate logs added, and then the powers come down to the front. Right, that's step two. And now step three is now that you have that, um, take the derivative of both sides. And on the left side, it's going to be um, the it's going to be, but what's it going to be? Let me reason with you. If you have the natural log of function, what have we learned is the derivative? Well, the derivative is 1 over the argument, right? 1 over whatever's in a natural log. But then chain rule says, yeah, but you got to remember to multiply by the derivative of what's inside there. So that's f prime of x. And so the way we like to write that is we just say, well, so therefore it's f prime of x. Here, it's f prime of x over f of x. So on the left side, this is going to become, it's going to become f prime of x over f of x. That'll happen every time on the left side. One more time. Why did that happen? Because the left side is ln of a function. And what's the rule for ln? It's 1 over whatever, right? Because that ln, I mean, that f of x is plugged in, right? This is, I should probably do it like that. Yeah, I should. That f of x is the plug-in. It's not multiply, right? This does not mean multiply. It's not product rule. Why not? Well, because for product rule, here's what it would look like. It would need to, if it was ln of x, f of x, that would be multiply. That would be multiply, and then we would use the product rule because that's an ln. This is his plug-in, and then there's an f of x multiplied outside of that. But like this, no, the f of x is not outside. He is the plug-in inside of ln. So that's not multiplication. That's f of x being plugged inside the ln. But you might wonder, well, how do you know? How do you know, Mr. Allen, that it doesn't have an x? Well, because what did I do on the first step? On the first step, I took the ln of, I probably should have said of both sides. I mean, I took ln of the left side and ln of, yeah, I probably should have done that, of the whole right side, right? I'm saying f of x equals, the original left side, right here, left side equals right side. So if two things are equal, then the ln of the left one must also equal the ln of the right one. So I put the f of x in there and I put the right side, I put the left side and the right side into an ln. That's what I did. That's how I know it's in there. I put it in there. On step one, I took the ln of it. That means put it in there. So when it comes to the derivative then, for ln, it's 1 over whatever's in there, but then chain rule times the derivative of the inside, which is f prime. Right? That's what I'm showing right here. Times f prime. So then that's over 1 just goes to the top, doesn't it? So it's f prime over f. So that makes sense. So the left side, you can just write that down in your notes. It'll always become f prime over f because it's 1 over the inside times the derivative of the inside. And that just is over 1, so it just goes to the top. Okay, now on the left side, taking the derivative, how are we going to do that? Keep this clean here. Oops, I didn't know. Um, on the right side now, this 2 will just stay sitting there times, and again, ln, so we know how that works. It's 1 over the argument. But again, because the argument is not a simple x, don't forget chain rule, times the derivative of the inside, which is just going to be 4. Chain rule. Right, because the 1 power comes down, subtract 1, it's gone, and then 5 is just 0. Plus, and then 3 just sits there times. And again, it's an ln. So it's going to be 1 over the argument. That's how you take the derivative of ln. 1 over argument. But chain rule says if the inside is anything other than simple x, you got to do the derivative of the inside, multiply. So what's that going to be? That's going to be 6x because that 2 comes down, subtract 1 from the power, and the 4 is gone. Okay, so we took the derivative. Now, we're not done yet. You might think, oh, so is that our answer? There we are. No, 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 because remember, what they're asking us for is f prime. And f prime is not alone yet. That left side is not just f prime, notice. It's f prime of x over f of x. So we actually have to get f prime of x alone. That's what they're asking us for. That's what we've been trying to get from the beginning. Find f prime of x. Well, how do we get f prime of x alone? Well, you multiply by the denominator. That's step number 4. So this was step number 3. Step number 4, multiply both sides. Both. My pen is losing. Both sides by f of x. This is always the steps we do for logarithmic differentiation. Yeah, because so I'll bring it down to make it more clear. So we have over, this is not so nice. Over there, it's more cleaner. Over f of x equal. Yeah, I'm going to put this 2 over 1, so I'm going to put it on the top, make it nicer. It's 2 over, suppose. Oh, wait, and the 4 is up there also. 2 and 4, so it should be 8. I didn't notice that. 8 over. Oh, with that little lump in, it's a 5. There we go. Plus, and yeah, the 3, you'll go to 3 over 1. These guys are all over 1. Go to the top. Do what, 18x up there? 18x 3 times 6x, 18x over 3x squared plus 4. Okay. So now, to get f prime of x alone, we're going to multiply both sides by f of x. So I'm going to go, okay. I'm going to go, let's do it in a different color here. I'm going to go f of x over 1, really, on this side, and f of x on that side. And it's going to cancel that out, huh? Right? And then what do we got? We've got f prime of x equals f of x. Now, what is f of x? Well, f of x is our original function, which is this. So, write it up, 4x minus 5 squared. Is that what it was? I'm forgetting. Yeah, 4x minus 5 squared times 3x squared plus 4 to the third. 3x squared plus 4 to the third. To the third times and then all of this. So that'll be, again, same old. Oops. Yeah. 8 over x minus 5 and 18x over bx squared plus 4. Boom, boom. So there is that, and that's our answer. We are done. Let me make this more a little more clear what just happened. So this f of x is right here. All of that is f of x, and then all that is right there. That's what f prime of x equals. You see how that ending part, I know it seems a little weird at the end. Let's recap real quick. So logarithmic differentiation. They're going to say that. You're going to have a couple of these. So how do we do it? Step one, we take the ln of both sides. There was no logs in the beginning problem. We take the ln of both sides. We put the left side in and ln and the right side in. That's logical, right? If two things are equal, f of x equals that right side, then if two things are equal, then the log of one of them's got to equal the log of the other. Okay? Why do we do that? Because there's all these nice log properties. That's what we do in step two. We say, oh, these are multiplied. You can just make that adding, and then the powers just come down the front. Look at that. No more powers, no more multiplying. Then take the derivative of both sides. On the left side, I showed how that's 1 over the argument times the derivative of the argument. So it always ends up being f prime of x over f of x. And then we take the derivative of each of this, which is pretty easy because it's just 1 over the argument times derivative of the argument. And then just step 4, multiply both sides by f of x because that'll cancel this out and get you your answer you're looking for. F prime of x by multiplying by f of x to cancel that out of the denominator. So you do that on the right side also, and there is f of x, the original function, times that. That is our answer. And so that's logarithmic differentiation.